Here are your video notes for lesson 8.1 about graphing linear equations. And our first example, we're going to focus on this information that the book's giving us. And it says that light travels faster than sound. That's why you see lightning before you hear thunder. The linear equation d equals 0.2 s, or 2/10 times s, expresses the approximate distance d in miles of a thunderstorm for a given value of s between the lightning flash and the thunder rumble. So if we come down here, for example 1, we're going to graph d equals 0.2s and determine whether it's linear. Well, from up above we already know that it is a linear equation. It will be linear, but we'll look at why is it linear. So in order to graph this, we first would be taking our number, our 0 for the number of seconds, and substituting it into our equation up here for s. And when we do that, we would get that the d, or distance, would be equal to 2/10 times 0, which equals 0. We can fill our table in there. And then we do the same thing with the 2. Find out that 2/10 times 2 equals 0.4. Fill in our table, and we'd keep going with the 4. And find out that that comes out to 8/10 of a mile. If we fill the 10 in, we get d equals 0.2 times 10, which equals 2. And for 15, we would get 3 seconds. So your table should be filled in now. Moving on, in this situation, distance depends on time, that we would be timing the distance or counting the number of seconds between the flash of lightning and the thunder. And from that, the distance the thunderstorm is away, we would be determining so that the distance away depends on time. And if we get that filled in, distance then goes on the y-axis, and time goes on the x-axis. And if we look at our numbers for the number of seconds that we have, or the time, we have 0 to 15. So across here we need to be putting in something so that it would start at 0 over here, but make it up to 15. And if we use the numbers and count off by 2's, we go 0, 2, 4, 6, 8, 10, 12, 14, and 16, and that will include all of our information then. For distance, we need to end up having it include just 0 to 3, so we probably can space it out a little bit more. And right here then, if we put 0, we can actually probably go by halves and have this be 1, 1.5, 2, so we can get those numbers written in as well. Now we're ready to plot our points, and if we look, this point should be plotted at 0, 0, 0 seconds, 0 for the time. Our next point, 2 seconds, should be plotted for 4/10 of a mile. The next one, 4, should be plotted at 4 seconds and 8/10. Our next one should be plotted at 10 seconds, should be at 2 miles away. And our third one should be for 15 seconds, that would be that the thunderstorm is 3 miles away. Now if we take a look, a blank is an equation whose solutions fall on a straight line on the coordinate plane. That would be a linear equation, which this is linear because the solutions do fall on a straight line. Now the next part of this says all of the solutions of a particular equation fall on that line. So if you're going to come up with any other combination of seconds and distance, they would have to be dots on this line. Also, all points that are on the line are solutions of the equation. It means if we wanted to put another point there, that should be a solution to our equation. And by the way, the line represents infinitely many points. You can keep putting points on. The arrow on the end of the line means that it goes on forever, so the dots could keep going right on off the page. If we take a look at this point right here that we had flashing, that point, let's see what it means that it is a solution to the equation. It means that if we figured out where are we at right here for seconds, we are at 5. And if we looked where are we at right now for miles, or distance, we are at 1. That would give us the coordinate point 5, 1. If we take the 5 and substitute it in for s, we would get that d equals 0.2, or 2/10 times 5. If we did the math, we'd get that d equals 1. So the distance is 1 mile there. So if it was 5 seconds between the flash of lightning and the thunder that you hear, you'd be looking at the thunderstorm being about 1 mile away. Now another way to think of linear relationships too is to consider its rate of change. And rate of change is a ratio that compares the amount of change in a dependent variable to the amount of change in the independent variable. If you will write this in with me, the rate of change equals the change in the dependent variable will be on top, the change in the independent variable will be on bottom. If we take a look at the table that we had from the first example dealing with thunder and lightning, the seconds should be considered to be the independent variable and the distance should be our dependent variable. So if we look to go from 0 to 2, it actually went up 2 seconds while the distance went up 4/10 of a mile. So if we write that as a ratio where we put the dependent variable on top and the independent variable on bottom, we get 0.4 over 2. If we look at the next gap, seconds goes up 0.2, distance goes up 4/10, we get the same ratio. If we look at the next one, 4 to 10, it gives us an increase of 6. The distance increases by 1 2/10 there. And if we look at the change in the seconds in the last one, from 5 to 10 it went up 5. The distance went up by 1 there, and we would get that that's actually a change of the dependent variable on top changed by 1 when the independent variable changed by 5. Well, to be linear, the rate of change must remain, and the key word there is constant. You may look at this and say, well, that looks like it's constant. That stayed the same. Well, what about these other ones? Well, if you divide the 0.4 by 2, you'll get that that equals 0.2. The next one equals the same. If we divide the 1.2 by 6, it also equals 0.2. And the 1.5, 1 divided by 5, actually will equal 0.2 or 2/10 as well. So there is a constant rate of change where that rate of change is 2/10. If we take a look at graphing another equation for our second example, y equals x squared, and determine whether it's linear, we would still once again take our values for x and substitute them into this equation. We would get negative 2 raised to the second power here equals 4. We can get that put in. And if we put the negative 1 in, remember that if you square the negative 1, you are going to be getting negative 1 times negative 1, and that's why these values in the table right now are positive for the y values. If you put 0 in and square it, you get 0. If you put 1 in and you square 1, you still get 1, 1 times 1. If you put 2 in and you square it, you get 2 times 2, which is 4. And if we look at plotting these on a graph now, our first point is at negative 2, 4. So counting that out over here to negative 2 and going up 1, 2, 3, 4, we get that point. Negative 1, 1 appears there. You guys should be plotting these with me. 0, 0, 1, 1, and 2, 4 gets plotted out here last. Well, I think we can look at this and safely say that is not a straight line. This is not going to be linear. So if you'll write this in as the last thing you're putting in on your notes, this is not linear since the points do not fall in a straight line. Thanks, and we'll see you tomorrow in class.